Complexity analysis, or the use of asymptotic notation to describe the efficiency of algorithms, is just a fancy way of realizing the goodness or the badness of an algorithm as per the resources those algorithms consume when applied on by some particular size of input. What resources do these algorithms consume, you ask? Well, the obvious being time and the less obvious being space. Yes, memory space. Why input size, you ask? Because the chosen algorithm might perform extremely well for a small sized input, but might just be terrible for a larger input, and that is pretty bad. Let's take an example of the linear search. It basically is the process of finding a particular required element in a whole list of elements by going through the list one by one and checking whether the element is present in that list or not. This might seem like a good idea when you have like 10 elements in the list, but what if you have like 100 million elements to search through? The computer has feelings too, right? So how do you compare algorithms? Well, one method is to write the algorithm down in a specific programming language like C, then compile it on a specific compiler like GCC, and then use a specific timer to check the running time of the algorithm. Do the same for all the other algorithms you want to compare, and pray to God your computer doesn't crash and burn. Do I really need to explain why this is a pretty bad idea? So we have asymptotic notations like big O, big omega, and big theta, as they specify a universal scale for measuring algorithms. And that, my dear friends, is amazing. But to implement some of these concepts, we have to make a few assumptions. One being that all elementary steps in the algorithms like addition, multiplication, division, subtraction take constant time. What is constant time? Well, it just means that to do all the included steps, the resources required are independent of the input size given to the algorithm. Not that in the real case scenario they don't matter, trust me they do, but while applying such algorithmic analysis steps, they're not as influenced by the input or its size for that matter. Even accessing an element in an array is considered to take constant time. If you know a bit about actual computer architecture, you might know that the time to access a given variable or array element is not necessarily fixed, for it could depend on whether the variable or array element is in the cache, in the main memory, or out on disk in a virtual memory system. Some sophisticated models of computers take these issues into account, but it's often good enough to just assume that all variables and array entries are in the same memory and they all take the same amount of time to access, hence constant time. The main thing you need to remember and understand is that algorithmic analysis depends on the growth of the size of input. I cannot stress that enough. Now, what would the complexity of the linear search be? As I said earlier, it's basically the process of finding a particular required element in a whole list of elements by going through the list one by one and checking whether the element is present in that list or not. In this case, we have the number of elements or our input size as n. Then it will take us about n amount of iterations to get the job done, assuming that is the average case. So this kind of algorithm has a big O of n complexity, where the big O is just a notation to indicate that in an average implementation of this algorithm, it will take n iterations to find the answer. But big O also specifies something else. It also enlightens us about the fact that it will never take more than n iterations to find the answer. Which brings us to the concept of bounds. The big O denotes the upper bound beyond which the consumed resources of the algorithm won't ever be exceeded. That's how you should think about the notations, in terms of resources and not in terms of time. So what if you find the element by linear search in the list at the first position? Should there not be a way to account for that in the algorithmic analysis? There is, and that is none other than big omega. Big omega specifies the lower bound and is in stark contrast to what the big O measures. Big omega is used to measure the lowest amount of resources used while running the algorithm, which in this case is big omega of 1, which is basically constant time. And that occurs when the element is present in the first element of the list. And it's constant time because it doesn't really need to worry about the size of the entire input because it is at the first position. It also has a say in the fact that these are the lowest amount of resources which can possibly be used to run this algorithm, and it is not feasible to run it without them. So that is what lower bound means. So now you might be wondering, so if big O measures the upper bound and big omega measures the lower bound, what in the world would the big theta measure? Big theta is just a mashup of both of them and uses big O to correspond to big theta of the upper bound and big omega to correspond to the big theta of the lower bound. That is absolutely it. So to make the concept more concrete, let us consider an example. Suppose you have an algorithm which runs a function of the input size as t of n is equal to 11n squared plus 22n plus 13. N here is the input size and the units of t of n can be whatever you want. Example, seconds or microseconds, it really doesn't matter. They are just consumable resources, and that's how you should think about them. Now as n grows, the term 12 and 22n become less and less significant. Imagine that n is 500, so well, n squared will be 500 squared, which if you ask me is a pretty large number as compared to 500. So you can now say that t of n is approximately equal to 11n squared, which has 11 and that is just a constant. So we can say again that t of n is equal to c1 times n squared, where c1 is a constant. As you can see the graph, for a value of c3 greater than c1, tn never exceeds the value of f2 of n in the horizontal direction, to the right I mean, which means that t of n is bounded by f2 of n, and more so, this is an upper bound. And as we saw earlier, an upper bound means using the big O notation. So the notation will be big O of c3 times n squared, but in most cases, as c3 is just a constant, it doesn't really reflect upon the input size, so we truncate it. Yes, the constant is considered in the real world timing analysis, but we get the final big O notation as big O of n squared, or O of n squared. Similarly, we can consider the lower bound with a value of c2, which is less than c1, by using the same assumptions and calculation we did earlier. We can say that after seeing the graph that t of n does not exceed the graph of the new function in the left horizontal direction and can be coined as being the lower bound. So this kind of a bound is labeled by the big omega notation, and in this case it is big omega c2 times n squared, after omitting the constant big omega of n squared. And now you must be thinking that if it is obviously graphed, big theta is basically between those two bounds, and by that you are probably correct. And so by now you must be thinking of how you might get a better understanding of algorithms, and to that I would recommend, or basically algorithmic analysis. And
today we're going to go over simple algorithm analysis, part 1. So we're just going to look at a few basic examples, nothing that includes recursion just yet. In the next video we're going to go over some more deeper examples that include recursion as well as Master's theorem. So let's get started. So why do we want to analyze an algorithm? Well, let's say you have a task of being in city A and you want to get to city B. You have a lot of transportation options available to you. You could walk, you could ride a bike, you could take the city bus, drive a car, or even fly. Some of these make sense over others. So for example, if you literally lived across the street from city B, you could simply just walk over, and that'd make a lot more sense than flying over. But if city B was across the country, it'd probably make a lot more sense to buy that plane ticket instead of riding your bike. In computing, algorithms are the same thing. So let's look at sorting, for example. If you want to sort a number of items from smallest to largest, you have a lot of different tools available to you, such as the insertion sort, selection sort, quick sort, binary, bubble sort, etc. Our ultimate goal in algorithm design is to complete the tasks that we want to efficiently. And by efficiently, we mean that it's quick in terms of time, as well as efficient in terms of space, because memory is limited in a computer system. We can't have the space fill up really quickly. So by analyzing algorithms, we can compare them, and then depending on the task, we can pick the best one. So what is running time analysis? Well, we want to determine the running time increases related to the size of input. So as input gets bigger, we want to see exactly what that does to the running time. Input is n values. Now we can't make any assumptions regarding n. In fact, we can't assume that n will always be small. It's probably best to assume that n would be adequately large. So with running time analysis and not making assumptions for n, this creates for a timeless concept that translates from old computing systems to modern machines. So let's look at some definitions. So the rate of growth is the rate at which running time increases as a function of input. Lower order terms. So when a given approximation of the rate of growth of a function, we tend to drop the lower order terms as they are less significant to higher order terms. Let's take a look at a simple example. Here we have a function. N cubed is a higher order term than n, which is a lower order term. So for simplicity's sake, when doing big O notation, we drop the lower order term of n. Therefore, the function has a big O of n cubed. Now let's look at that in layman's terms. Let's say you were to buy a house, and along with the house, you were to purchase a lock. If you spent $400,000 on the house, but only $1.99 on the lock, if someone asked you, hey, how much did you get your new house for? You would unlikely say $400,001.99. You'd likely say just $400,000. Because the $400,000 is significantly larger than the $1.99, it's safe to put less significance on that $1.99 like we do with lower order terms. There are three major ways to analyze an algorithm. There's the worst case, the best case, and the average case. The worst case is the longest time, and it's represented by big O notation, which is drawn like this. The best case is the least amount of time, and average case is the average amount of time. Best case is denoted by omega notation, and it's written like this. Average case is denoted by theta notation, and it's written like this. Most of the time, we do use the big O notation because it's the most practically useful one of the three. Best case, we can't always rely on because it's not always going to be the best case. And average case is less useful than the worst case. So what we always think about is to plan for the worst and hope for the best. So with big O, once again, we hope for the best and plan for the worst. So let's look at this function here. Let's determine what its big O notation is. Let's define the highest order term as g of n. So what is g of n in the above equation? Well, g of n is equal to n to the power of 4. So the function of big O of g of n is big O of n to the 4. Is it always best to use big O notation? Most of the time, yes. However, if big O of n is equal to omega of n is equal to theta of n, then we tend to use theta of n. It's just a formality and it's widely practiced. So let's now look at some examples of algorithms and determining what their big O notation is. So if we look at this simple for loop here, on the inside there's a constant operation, a simple addition. On the outside there's a loop that happens n times. So our function is the constant times n, which is the amount of times that happens. The leading constant is typically ignored. So our function has big O of n. Let's look at another example. Now this one's slightly different. We notice that the constant operation is still the same in this. However, the loop goes to n over 2 times, so it doesn't quite reach n. So our function is c times 1/2 times n. The c and the 1/2 are constants, and the n is the loop. And remember, the leading constants are ignored, so our function of n, running time, is big O of n. Even though the loop iterates half as much as the last example, they're still both O of n. Now let's look at something more interesting. So we have our constant time operation in the middle that happens n times thanks to this inside loop. That whole package on the inside happens another n times because of the other loop. So our function is c times n times n. C is the constant, the first n is the inner loop, and the last n is the outer loop. We can simplify this by having f of n is equal to c times n squared. And we can drop that constant, giving us big O of n squared. Now let's look at consecutive statements, statements that are one after the other. Let's label the top part as 1 and the bottom part as 2. We see that the top one, number 1, is a single loop operation, and the bottom one is nested loops. So writing out the formula, we have f of n is equal to c times n plus c times n times n. The c times n is the number 1, and the c times n is the number 2. We can simplify this by merging those two n's at the end and putting a square symbol above. And we notice that c times n squared is the higher order term in this case, and that's what takes precedence, so that the function of n has a big O of n squared. Now let's look at an if then else statement. And let's build it as we go through. So looking at the statement, we have a constant in the if condition. So that's a C0. If the if condition is met, then another constant occurs. That's C1. However, with the else, there's actually a looping structure on the inside that goes to n, and an inner loop inside of that first looping structure that goes to n, as well as a constant. Simplified, the function now looks like this: C0 plus C1 plus C2 times n squared. N squared is the higher order term here, so our f of n has a big O of n squared. So those are just a few examples of how to analyze some simple algorithms. Now here are some tips when analyzing. Be mindful of where loops start and end, especially for nested loops. If the best case, average case, and worst case are equal, use theta. And know your orders when looking for the highest order. This is something that's good to practice and good to understand. So which term is the highest order in the following equation? If we look at this, we have f of n is equal to n factorial plus 2 to the 2 to the n. Now n factorial we know can get really big at relatively high values of n. But it doesn't necessarily look like 2 to the 2 to the n would be bigger than n factorial for a large enough given n. But actually, when we graph it, we see that the red line here, which is 2 to the 2 to the n, is a lot greater and rapidly increases faster than the n factorial, which is represented by the blue line. Therefore, the highest order term in there is 2 to the 2 to the n, giving this function a big O of 2 to the 2 to the n.
The agenda of the session includes how to evaluate an algorithm, what is the space complexity, what is time complexity, and how to calculate them with examples. The first question comes to our brain is how to evaluate an algorithm. Any algorithm is evaluated based on their performances. The performance evaluation can be done in two different ways, either before the execution of a program or after the execution of a program. Before the execution of a program, it is termed as priori estimate. It is also known as performance analysis. Once it is executed as a program, then we are analyzing the performance. It is termed as posteriori testing, also called as performance measurement. Performance analysis mainly deals with the time and the space required for the execution of an algorithm. Hence, we focus mainly on time and space requirements for the algorithm. This performance analysis includes the calculations of time complexity as well as space complexity. Let us see what is space complexity. The space complexity of an algorithm is the amount of the space, that is the memory, required by the algorithm to run to completion. This space required is a sum of two components. It may be either a fixed space or it may be a variable space. Fixed space is independent of input and output supplied to the algorithm. Example, instruction space. The number of instructions will be fixed. Space for the variables. The variable space is also fixed. The space for the constant, which is also fixed. Such space requirements come under fixed spaces. The other one is variable spaces. This is absolutely depending on the problem which we are solving. Example, reference variables. The reference variable spaces vary based on the problem. Similarly, recursion stack space. The recursion stack size depends on the number of times of recursion. Hence, these two spaces are depending on the problem instance. They can be termed as variable space. Now, if I assume P is an algorithm, S of P is the total space required for an algorithm, then S of P is equal to C plus SP, where C is nothing but a fixed space which is always constant, and SP is the variable space which varies depending upon the problem. So when we analyze the space complexity, we majorly focus on SP, that is variable space, but not on the fixed space. This variable space is absolutely depending on the instance characteristics. Let us see with an example. Consider the example algorithm to calculate sum of n elements in an array A. Now, in the example, we require a space to store the variable value n. Let me assume the space required is 1 word. We require space to store n values in an array. Now, the size of the array will become n. So, therefore, we require n words to store the array. We do have a loop variable I which is iterating from 1 to n. Therefore, I require to store the value of I require space 1 word. We are calculating sum in the variable s. So, to store it, we require 1 word space. Now, the total size required is n plus 3 words. Hence, I can say that the space required to calculate the sum of n numbers in an array will be greater than or equal to n plus 3 words. Let us see an example of recursion. Let us implement the sum of array of n elements using recursion algorithm. If n is less than or equal to 0, the return zeros. Else, I will calculate a of n plus recursion sum of a of n minus 1. Now, in this case, the space requirements are as follows. Any recursion call involves the space for local variables, the space for return addresses, as well as the pointer. Here, R_sum is a recursion call. It requires the return address, that is 1 word, and a pointer to point an array, 1 word, and has a local variable n which requires 1 word. So, every call for recursion sum requires 3 words. How many recursions do we call? For the sake of calculation of n elements, we require n plus 1 recursion calls. That is, the depth of recursion is n plus 1. Now, the total space required is n plus 1 recursions, each of having 3 words, a total of 3 into n plus 1. Hence, I can say that the recursion sum for calculating the sum of n elements in an array will be taking 3 into n plus 1 steps. Let us see now what is time complexity. It's very simple. The time complexity is nothing but the total computer time taken for completing our algorithm. Now, time complexity also has 2 components. One is the compile time and runtime. The compile time will never depend on the input or the output being supplied. That is, it is not depending on instance characteristics. And as we all know that once a program is compiled, it can be run several times without any compilation. Hence, I can say that compile time is constant time. Come to the runtime. The runtime always depends on the input and outputs. That is, it always depends on the instance characteristics. It depends on the problem instance. Hence, it is a variable time. So, the time complexity is calculated as runtime plus compile time, where compile time is constant. If I assume P as an algorithm, T of P is the time complexity, it can be given as sum of C plus Tp, where C is the compile time and Tp is the runtime. How to calculate time complexity? One of the easiest methods to calculate time complexity is count the number of steps. for each statement in the program. What is a program step? A program step is nothing but a meaningful segment in a program that has an execution depending on instance characters. Note that all the statements in the program may not have executions all the time. So we are bothered only the executable statements in the program. First, identify the executable statements in the program. After identifying the executable statements in the program, count the number of steps for each program statement depending on kind of statement. Then, how can I count it? For example, if it is a comment, it is not being executed at all and it takes 0 steps. If it is an assignment statement, it takes only 1 step to assign the value. If it is a condition, to check the condition, it takes only 1 step. If suppose it is an iterative statement or a loop, to reiterate n times, it takes n plus 1 steps, where n steps will check the true condition and n plus 1 step will check the false condition. When a loop is having n plus 1 step, the body of the corresponding loop will execute for n steps. Based on this number of steps for each program statement, we can calculate the time required for an algorithm. Let us see the examples. The first example, the algorithm for calculation of sum of array elements. The first line is not executed, hence it is written as 0. The second line is also not executed, hence it is written as 0. The third line, s is equal to 0, is an executable statement. For I is equal to 1 to n is also an executable statement. S is equal to s plus a of I is also executable statement. Return yes is also executable statement. Closing braces is not an executable statement. Initially, we identified the executable statement. Now, let us try to find the frequency of each executable statement. S is equal to 0 is an assignment statement. Hence, the frequency is only 1 step. For I is equal to 1 to n is an iterative statement. Hence, the frequency is n plus 1. S is equal to s plus a of I is an assignment statement which is n corresponding to the loop. Hence, it is executed n times. Return s is a returning statement which returns a value. Hence, it is executed 1 time. Now, let us calculate the total steps. 1 into 1, 1, 1 plus 1 into n plus 1, n plus 1, 1 into n, 1 into 1, 1. A total of 2n plus 3. The total time required is 2n plus 3 steps for this algorithm to calculate the sum of n elements in an array. Let us take one more example. This example is used to add the sum of two matrices A and B of order m into n. The first two steps are not executable. The loop is executable step. The jth loop is also executable step. The calculation is executable step. For I is equal to 1 to m, this loop executes m plus 1 times, and the body of the loop, both statements will execute m times. But in the body, there is another loop for j is equal to 1 into n. It also executes n plus 1 times. Its body, c of ij, will execute n times. Hence, the total will be 2mn plus 2m plus 1 steps. Now, let us see how to calculate the time complexity for the sake of recursion algorithm. If I consider recursion sum for the n elements in an array, if there are no elements, then return 0. If there are more elements, you calculate a of n plus recursion sum. The executable steps are, if n equal to 0 is executable step, return 0 is executable step, return r sum of a n minus 1 plus a of n is an executable step. Here, there are two conditions. If n is 0 or greater than 0. Now, consider the case where n is equal to 0. If n is equal to 0, this condition is verified, so it is executed 1. As the condition is true, therefore it is returned 1. And the other statement is not executed. Hence, the total number of steps required when n is equal to 0 is 2. If suppose n is greater than 0, the condition is checked once. As the condition is false, the statement is not executed. Then we are going to the return statement of Rsum. This statement is executed one time. But how many times it executes? 1 plus x time, where x is the time taken for this recursion sum. That is t of n minus 1. Therefore, the total time taken when n is greater than 0 is 2 plus x. Put it in a word, if t of n is the time taken for this algorithm, it will be 2 when n is equal to 0 and 2 plus t of n minus 1 when n is greater than 0.
Hello and welcome back. In this video, we will discuss time complexity of bubble sort algorithm. Let's get started. First, let us recap bubble sort algorithm. Bubble sort is used to sort an array with n number of elements. Sorting takes place by stepping through all elements one by one in pairs and comparing adjacent elements and swapping elements in a pair that is out of order. It is called bubble sort because in each iteration, the largest element in the array bubbles up towards the last position, just like a water bubble rises up to the water surface. The next iteration bubbles up the second largest element and so on. Meanwhile, smaller elements bubble down towards the first position in the array. This continues until the array is completely sorted. Okay, now let us see the time complexity of bubble sort. This is the pseudocode for bubble sort algorithm. The basic operation is the comparison operation. It is the statement that checks if j plus 1th element is less than jth element or not. There is no precondition before this statement, so it executes in every iteration of the two for loops. The frequency of its execution depends purely on the size of the array. There are two for loops in this algorithm. The inner for loop executes as long as the value of j ranges from 0 to n minus 2 minus I. How many times does the basic operation execute in inner loop? It is given by summation of 1 from j equal to 0 to n minus 2 minus I. This has to be multiplied by the number of times the outer for loop executes. So we multiply this by summation I equal to 0 to I equal to n minus 2. This whole expression gives us C of n, that is, the number of times the basic operation executes. Let us calculate this. First we will simplify the rightmost summation. It is n minus 2 minus I minus 0 plus 1, which is nothing but summation of n minus 1 minus I, where I ranges from 0 to n minus 2. Let us split this into two summations, one of n minus 1 and another of I. The range of I value is same for both. For the first term, we take n minus 1 out. So it will be n minus 1 multiplied by summation of 1, where I ranges from 0 to n minus 2. If you carefully observe the second term, you can see that it is summation of n minus 2 consecutive numbers. We all know that sum of n consecutive natural numbers is equal to n into n plus 1 divided by 2. Similarly, here n is n minus 2, which we multiply by n minus 1 and divide by 2. This is the simplified expression. Ignoring the constant, we see that it is of the order n square. For all kind of input, bubble sort is of the order n square. That is, the time complexity of bubble sort is theta of n square. It is same for best case, average case and worst case scenarios. So that's all about bubble sort time complexity. See you in the next lecture.
So if we remember our integer array from before, we said the data in it is unsorted, that is to say it's not in any particular order, whereas when we're talking about sorting the data, what we want to do is get it in ascending order, that is to say smallest to largest number left to right. So as a human being, it'd be easy to do that particular array just by inspection, whereas if the array was 100,000 elements long, it would be much more difficult for a human being to sort it. So we need to develop algorithms or recipes to do the sorting. And the simplest and most common algorithm that people learn first is called bubble sort. Bubble sort works as follows. For an array of size n, we just look at the first two elements and we check if the first element is bigger than the second. If the first element is bigger than the second, we swap it. If it's not, we don't do anything. Then we look at the second and third, then the third and fourth, the fourth and fifth, and we check if the left element is bigger than the right in each case. If the left is bigger than the right, then we swap them. If they're in the right order already, the two elements, then we don't do anything. We keep on doing that until we get to the end of the array. That doesn't mean the array is sorted though, so we jump back to the start again and do that whole process again and again and again until the array is sorted. Let's think about the swapping bit for a second. If I want to swap two values, the following approach will not work. If I have the first element and I assign the value from the second element to it, and then I assign the value from the first element to the second element, that won't work. Because if we think about it, if we say that the first element's value is 44 and the second is 23, if I say the first element now gets the value of the second one, so if the second is 23, the first is now 23, that means they're both 23 now. So then if I try and say that the first element gets the value of the second, or the second gets the first, they're all 23. So we've lost the number 44 completely, so that swap doesn't work in that way. What we need is an extra variable to make this work. Let's call it temporary value, and that temporary value will store one of the values so that the swap will work. So let's say we give temp value the value of the second element, and then we say that the second element is overwritten by the first element's value, and then the first element gets the value of temp value, then the swap will work. Let's imagine our values again. 23 is stored in temp value, 44 is written into the second element, and then 23 is written into the first element. So then we have a successful swap where first element is now 23 and the second is now 44. So if we want to see the if statement that goes around this for bubble sort, for the first two elements, it's if the second element is less than the first element, then we do the swap. So if the second is less than the first, do the swap. And there's no else needed, because we do nothing if they're in the correct order already. We could generalize that to if n minus 1 is less than the value in n, or even index plus 1 bigger than index. And in all of these cases, if the element on the left is bigger than the element on the right, we swap, otherwise we don't. If we want to go from the start to the end of the array in pairs, we note that the array goes from 0 to n minus 1. So the loop goes from 0 to n minus 2, because that'll compare 0 to 1, 1 to 2, 2 to 3, so on up to n minus 3 to n minus 2, and then n minus 2 to n minus 1. So it'll compare all the elements to each other, because index will go and compare n minus 1 to n minus 2. That's index to index plus 1. So that doesn't mean the array is sorted just because we do that once though. One pass doesn't get it done. Here's an example. We start off, we compare the first two elements. Is the left element bigger than the right? Yes it is, so we swap. We look at the next two elements. Is the left bigger than the right? Yes it is, so we swap. Do it again. Is the left bigger than the right? Yes it is, so we swap. We do it again. Is the left bigger than the right? Yes it is, so we swap. We do it again. Is the left bigger than the right? No it's not, so we don't do anything. We check the next pair. Is the left bigger than the right? Yes it is, so we swap. And finally, is the left bigger than the right? Yes it is, so we swap. So now we have not sorted the array, but we have pushed the largest value, 54, to its correct position, because it's at the top of the array now. So if we do that again, 23 and 42 are in the correct position, so we don't do anything. 42 and 33 swap. 42 and 16 swap. 42 and 44 don't do anything. 44 and 34 swap. 44 and 18 swap. And 44 and 54 are fine. So what happened there? We've pushed the second largest value, 44, into its correct position. Next time around, compare those two, no swap. Compare those two, swap. Compare the next two, no swap. Compare the next two, and we swap. Compare the next two, and we swap. And everything else is as is. So we've pushed the third largest value the next pass around the array we've done. Let's try it again. 23 and 16 we swap. 23 and 33 no swap. 33 and 34 no swap. 18 and 34 we do swap. 34 and 42 no swap. 42 and 44 no swap. And 44 and 54 no swap. So we've pushed 34 into its correct position. Let's do it again. 16, 23, no swap. 23, 33, no swap. 18, 33, we swap. And then the rest, there's no swaps. So we've pushed 33 into the correct position. If we do it again, 16, 23, no swap. 23, 18, swap. 23, 33, no swap. No swap. No swap. No swap. And no swap. So now we have moved the sixth largest value, 23, into its correct position. Let's not bother doing it again though, because the array is sorted now. So 16, 18, 23, 33, 34, 42, 44, and 54 is all sorted now. So we need one loop that is going from the start to the end of the array, and then an outer loop around that which says keep doing that n times. So from 0 to n minus 1. So go from start to the end of the array and go back to the start again and do it again, and do it again, and do it again, and do it again, and keep doing it until the array is sorted. And that is what bubble sort looks like. So our pseudocode program bubble sort, declare the integer with two loops, a for loop, that's the outer one that goes from 0 to n minus 1, and then the inner one, which is 0 to n minus 2. If the inner index, if the value on the right is smaller than the value on the left, swap them around, otherwise do nothing. Keep doing it and you'll have your array sorted. Here's a visualization of it. It gets sorted from the top all the way down.